T-minus 17 seconds and counting. 15, 12, 11, 10, 9, 8, 7, 6, start, 2, 1, boost ignition, and liftoff of the Space Shuttle Discovery, returning to the space station, paving the way for future missions beyond.
All right, welcome to episode 3 of Space Crew Junior. My name is Alex Morrison, and I'm a sophomore mechanical engineering major at the South Dakota School of Mines and Technology. And I'm here to talk to you about the International Space Station, but more specifically the Columbus Lab, and we'll also take a little bit of a turn and talk about Newton's law of universal gravitation. So like I said, we're going to talk about the Columbus Laboratory module on the International Space Station, and then we'll go a little deeper and talk about what experiment racks are and those that are aboard the Columbus module. Next, we'll take a dive into the actual experiments they're doing in these modules. And finally, like I said, we'll take a bit of a detour and we'll talk about Newton's law of universal gravitation, because as we all know, gravity is very important. So first, let's even take a look at where is the Columbus Lab module on the International Space Station. So if we take a look at this picture right here, we can see there are 3 main laboratories. On the left there, which is what we're focused on, is Columbus. So you can see it kind of jutting out on the very far end there. And if we take a look at the other 2, we can see that there is Destiny, which is NASA or the United States laboratory module, and on the right there is Kibo, which is Japan's research laboratory, and Reese discussed that one in the previous episode of Space Crew Junior. But what even is the Columbus Laboratory module? So as I said, it is one of 3 main lab modules on the International Space Station, and it was the one that was created by the European Space Agency, which is essentially Europe's version of NASA here in the United States. And it was actually the first permanent European research facility in space, which is just a pretty cool fact. And it was manufactured by a company called Thales Alenia Space, which is a French and Italian aerospace manufacturer based out of Cannes, France. And they are the largest satellite manufacturer in Europe. And if you take a deeper dive into how big Europe is, that means that they make a lot of satellites in proportion to how many people there are there. And although it is a European product, it was actually launched aboard NASA's Space Shuttle Atlantis, and that occurred on February 7th, 2008, so about 14 and a half years ago now. And although from these pictures that it looks just absolutely massive, these lab modules, or at least in the case of Columbus, are not as big as you'd exactly think. In terms of Columbus, it has a length of about 23 feet, which isn't all that long. It's less than 10 yards on a typical football field in those 10-yard increments. In terms of diameter, or from each end to each end, in terms of width, it's about 15 feet. And if you're curious what that is expressed in volume, it is 2,646 cubic feet of space. And also, if you're curious just how much this thing would weigh here on Earth, it has a total mass of about 22,708 pounds. So although it isn't massive, it is pretty heavy. And where did it even get its name, Columbus? Well, you could probably guess that they named it after Christopher Columbus, which is the well-known explorer from Genoa, Italy. And why did they decide to name it after him? Although it's kind of hard to find why they did, one could reasonably assume that it is because it is an ode to exploration, which is what Christopher Columbus was known for. And as opposed to the confines of Earth, this lab can aid in the exploration of space, which is what us humans are trying to do. So now we'll go on to our next subject, which is experiment racks, what they are, and the ones that happen to be on board Columbus. So experiment racks are formerly known as International Standard Payload Racks, or ISPRs for short. And they are essentially containers used by all members of the International Space Station, which makes it easy for them to switch them out depending on what experiments need to be done in different lab modules. And if you take a look at that picture there, that is a rendering of the Columbus Biolab rack, which we'll actually discuss a little bit later in the episode. But these racks are not all that big. They're only about 6 feet tall, 3 feet wide, and about 2.5 feet deep, even smaller than an old school telephone booth. And like I said, since they're pretty small, Columbus can actually hold about 10 of these. And I believe it is 8 in its walls and 2 in its ceilings. And although it has room for 10, there are 5 notable ones that are most commonly discussed in the field of science. So the first one, like I just mentioned before, is the Biolab, which essentially involves experiments on microorganisms. The second one is the European Physiology Modules Facility, and this essentially investigates the long-term effects of spaceflight on the human body, because as humans are not exposed to gravity for long amounts of time, certain things happen to our muscles and our bones that are noticeably different once they get back to Earth. The third of these racks, which we'll also discuss a bit later in the video, is the Fluid Science Laboratory, and this involves experiments that are looking into how liquids react in essentially zero gravity, which is what there is on the International Space Station. The fourth of these is the European Drawer Rack, which is actually very modular and can be adapted for all kinds of experiments. And the final one is the European Transport Carrier. And although there's actually not any experiments that are done with this ISPR, it actually accommodates items for storage and can also simply act as a workbench if one of the astronauts on board the International Space Station needs more area to do what they're doing. So now that we've discussed a few of the notable ISPRs on the Columbus Lab, we're going to take a look into 2 of the experiments that I think are really interesting that they're doing in the Columbus Laboratory module. So the first of these is called the Rotifer B study, and this is taking place in the Biolab rack, which we previously discussed. So what even are rotifers? Well, they look something kind of like this. They are very, very small microorganisms that are usually about a millimeter or much less in size. And they are also commonly referred to as wheel animals, but for the sake of this discussion, we'll keep referring to them as rotifers. And they are considered masters of survival. They can be found in any body of water on Earth, no matter how big or small that body of water is, from something like a small puddle from rain to any of the Earth's oceans. And what this experiment does is it makes use of a certain species of rotifer called a deloid, which are extremely resistant to radiation. And what they're doing in this experiment is they're first taking some of these deloid rotifers on Earth, they're drying them and putting them on a certain type of gel, and then they expose them to very high amounts of radiation, essentially from an X-ray, like how you get an X-ray when you go to the hospital for a broken bone. And once they've exposed them to all of this radiation on Earth, they are then sent to the International Space Station and to the Columbus Laboratory module, where they are rehydrated with a mixture of water and lettuce juice. And once they are rehydrated, they are then put outside of the module to be exposed to cosmic radiation for a pre-established amount of time. And while that's taking place, it actually freezes them because space is so cold. And finally, once they've exposed them to all this cosmic radiation and they're frozen, then package them back up, send them back down to Earth, where scientists kind of take a look at them and kind of examine their ability to actually regenerate their DNA, because throughout all of this process, they do not die. Their DNA gets severely damaged, but they are always able to fix it. And this kind of begs the question, why is it so important? Well, the first thing is we want to protect our astronauts because they are exposed to over 200 times more radiation than us humans here are on Earth. And so the best way that this experiment can help is actually improve or give us better insight to improve the protective layers on spacecraft for these astronauts that are exposed to prolonged radiation. And the other thing actually occurs on Earth, which is giving better protective or developing better protective equipment for medical professionals, especially those that administer X-rays to people, like I said, with broken bones, or simply administer radiation therapy to cancer patients. So The next experiment we want to talk about, which takes place on the Fluid Science Laboratory rack, is the multi-scale boiling experiment. And just for some context, what even is boiling? We hear people talk about it all a lot, but no one really gives us a really straightforward definition. So the most simple terms I can put it in is it is heating a liquid to a high enough temperature where it then essentially vaporizes and turns into a gas. And a common example of this is, let's say you growing up, your parents are making spaghetti. Well, to do that, they have to cook the spaghetti noodles, and you'll usually hear it, and you'll ask them, what's that sound coming from? And that is the boiling pot of water that is on the stove. And they'll tell you not to put your hand above that pot, and there's a reason why. They want you to be safe. Although it looks harmless, this boiling that's happening is raising the temperature of the water so high that it turns into a gas, and it turns it into, the case of water, steam. And steam is very hot, and that's why they don't want you to put your hand above it, because it can burn you. But the experiment itself is also sometimes referred to as Ruby, but it aims to expand our knowledge on the process of boiling. And it is important to understand how the boiling process works in weightlessness like that on the International Space Station, because gravity does play a big role in boiling. And you can see from this figure, and this is actually what they're doing with this experiment, is they're boiling water and then allowing those bubbles that are created to go through a very small hole. And you can see that the bubbles move much quicker on high gravity, but move very, very slowly in low gravity. And the reason why experiments like this can't be done on Earth is because these bubbles move too fast, and scientists can't take the time to examine them and see their shape and how they react. Whereas in zero gravity in space, like that on the Columbus module of the International Space Station, these bubbles move so slow that they can really take a good look at them and figure out just what exactly is going on. And some goals of this experiment, mainly cryogenic fuel storage, which for those of you that don't know, is essentially cryogenic means rapid cooling or cooling to a very low temperature, because when you cool liquids or most items, they actually contract and they become smaller, meaning in the case of fuel, you can actually hold more of this fuel. And this could be really good for long space flights. Humans are trying to get to the moon right now, and to do that, we need a lot of fuel to power whatever rocket is going to do that. The other thing that scientists are looking into with this experiment is simply more efficient cooling of electronic devices, both those here on Earth and in space. As we know, or if you ever have used a computer and you hear a fan start going in it, or it feels very warm on the bottom, that's because as electronic devices are being used, they generate a pretty large amount of heat, and especially in space, we need to get rid of this heat very quickly, and boiling is the most efficient way to do that. And even this scientist who I have a picture of here for the European Space Agency, his name's Daniele Mangini, he says, boiling is an extremely efficient way of getting rid of excess heat. This research could therefore provide very valuable information for improving the thermal management systems in space as well as terrestrial applications. And as mentioned before, we're going to take a little bit of a detour and actually talk about Newton's law of universal gravitation, because gravity is very important. So this law simply states, or not simply, but it states, every particle in the universe attracts every other particle with a force along a line joining them. And it is given essentially by this equation, which does look very complicated, and to be fair, it somewhat is. This equation is simply saying the force of gravity between two objects is equal to Newton's gravitational constant, which is this long number you can see here, multiplied by the mass of the first object by the mass of the second object, and then you take all of that and divide it by the distance between the two objects squared. And in more simple terms, this equation is saying, or Newton's law of universal gravitation is saying that any two objects in the universe will attract each other, and you can use this equation to find how strong that attractive force is. And this plays a huge role in our exploration of space and even our knowledge of space so far. There's a reason why the moon is constantly orbiting Earth, and that is because the gravitational force between the two objects keeps them close together. And some examples of this. So you might ask yourself, or I'm going to ask you, Do you like watching TV? Well, if so, then TV requires the use of many satellites, and these satellites need to be kept in a constant orbit around Earth. And Newton's law of universal gravitation helps us because it helps us determine how far away from Earth's surface that these satellites need to be. If they're too close, as they orbit more and more, they're going to get closer to the Earth's surface and eventually crash. And if they're too far away, then they're eventually just going to float off into outer space, which we don't want. So as long as we can kind of figure out the gravitational force between that Earth is putting onto the satellite, then we can keep it near us. And a second example of Newton's law of universal gravitation has to do with high and low tides, like that commonly seen on beaches. So what high and low tide is essentially at different times of the day, the water is going to be much higher, as in high tide, or it's the other times of the day, it'll be in a low tide. And that is essentially the water is much, much more shallow. It's much further away from the beach itself. But anyway, so why does this even happen? Well, this happens because of, again, the gravity that the moon exerts on the Earth, and which can be explained by Newton's law of universal gravitation. So when when the moon is at a certain point relative to Earth, any water that's in a straight line across from that surface of the moon that's closest to the Earth will be in high tide, which can be seen from this picture. And the opposite points, or essentially those points that are perpendicular, will actually be in low tide. And Newton's law of universal gravitation, again, it helps us because we can kind of figure out where there is going to be high tide and where there's going to be low tide at certain times of the day, because we'll know where the moon is going to be at that time of day, and that can help with safety procedures on beaches because you don't want someone wandering into the water not realizing it's about to get much deeper. So to conclude, we've talked about the International Space Station, but we took a much closer look at the Columbus laboratory module made by the European Space Agency. These experiments are always super interesting. There's just hundreds, if not thousands of them going on, and they're not just doing these because they think it's cool. They also serve great importance to us. We're constantly trying to figure out ways to improve technology here on Earth, as well as technology that we need in space. Like I said, humans are doing their best to try to get to the moon, and to do that, we need rockets that can get us that far distance away. And also Newton's law of universal gravitation, very important, just like gravity, because gravity, at least in terms of what happens to us humans here on Earth, actually keeps our feet on the ground, and it is the reason why all of our water is where it is, why water flows down instead of up, and knowing how gravity acts between two objects is very important in terms of, let's say, two planets. But other than that, thank you for watching my part on the International Space Station's Columbus module. And we're also going to have Macy discuss NASA's Destiny laboratory module. Thank you.
Hi, my name is Macy Fliehe. I'm a sophomore mathematics major at the South Dakota School of Mines and Technology. And I'm here at the Journey Museum and Learning Center to teach you a little bit about Destiny, which is a research laboratory on the International Space Station. So Destiny is the US-owned research lab on the ISS that was created and built by NASA. It is about 28 feet long with a 14-foot diameter, which is about the size of a small school bus, but it is a little bit wider than that. The Destiny laboratory is unique because it is within microgravity. Microgravity means that there is very little gravitational pull from the Earth. There's only enough to keep the ISS orbiting, but not enough for the astronauts to actually feel it. Now I'll show you a few pictures of Destiny so you can get an idea of what a research lab in space actually looks like. So this first picture is Destiny being attached to Node 1, which was called Unity, in 2001 when it was first brought up to the ISS. These next two pictures of two different astronauts. The one on the left is from 2007, when they added external storage to the Destiny module, and the right is from 2017 of an astronaut tethered to the side of the Destiny module. This picture is from inside the Destiny module taken in 2019, and you can see all of the different technology and equipment that is being held on the Destiny laboratory. And this final picture is a diagram of the ISS, and you can see Destiny circled right now down near the bottom, and you can see node 1 and node 2 on either side of it. So why did NASA choose to name their module Destiny? Well, NASA has had a couple of rules for naming their modules since they started adding them to the ISS. The first rule is that it cannot be named after a person. The second is that it must have a clear and appropriate meaning behind the name, and that it must sound different or unique from other modules that they've added to the ISS. Destiny refers to the future, and the lab is used to help future space exploration, so it was the perfect name choice for the lab. Now we will talk about a few experiments that are held in the Destiny laboratory, starting with the Combustion Integrated Rack, or CIR. The first experiment is ACME, the Advanced Combustion via Microgravity experiment. This experiment tests how fire spreads and how it reacts in microgravity, which is a little bit different than how it does on Earth. The second is FLEX, which tests new flame suppressant materials for use on spacecrafts, but also for use on Earth for firefighters. The third is SOFIE, which tests and assesses the risks of fire on manned spacecrafts. And the last is CFI, or the Cool Flames Investigation, which is learning about the newly discovered phenomenon of cool flames, which is fire that is not very hot and is actually invisible to the naked eye, that they recently discovered in microgravity. So why are we doing the experiments on the Combustion Integrated Rack? Well, all of these experiments are to ensure safety on spacecrafts and on Earth. Finding new flame retardant materials is very important on spacecrafts, but also for firefighters on Earth. Putting out fires is also a very big important thing, and finding new ways to put them out that is safe for astronauts in space. And fire in microgravity acts a lot different than it does in gravity, so it's important for us to know how it will work. It's also very important for us to learn safety on manned spacecrafts. The second we will talk about is the Human Research Facility. The Human Research Facility is also on Destiny, and it has a lot of exercise equipment, a scale that measures weight in microgravity. It has ultrasound equipment and cold storage, just to name a few of the few things that are on the Destiny laboratory. This is being researched to understand the long-term effects of space on astronauts and how long-term space flights will affect their bodies. So now that we've learned about research on the Destiny laboratory, I'd like to talk to you about the scientific method, which scientists on Destiny are using, as well as scientists here on Earth, and you can use at home. The scientific method starts by asking a question. The scientists on Destiny asked, how can we come up with more flame retardant materials or better ways to put out a fire on a manned spacecraft? These questions will lead you to finding information. Before you start doing experiments, you have to research your topic first and get an idea of what you're going into. And then you must make a hypothesis. A hypothesis is just a guess. So the scientists may have guessed maybe this chemical would work best for putting out a fire on a spacecraft, rather than what we use on Earth, because they researched what we use on Earth. Next is the biggest portion of the scientific method, which is testing with experiments. This is what scientists are doing every day on the ISS and even on Earth. This leads to data that they collect through their experiments, and you have to analyze it to decide if your hypothesis was correct or not. And this leads to making a conclusion, which is answering the questions shown by your data. So you can say that, yes, this chemical did work to put out a fire, but maybe it didn't, and it did something different than you expected. And this leads to more questions. And we can see that the scientific method is a cyclical system, and that there are always more questions to be asked, and there are always more things to learn. So what did we learn today about the Destiny Lab? We learned about the different experiments and equipment that are held on the lab, such as SIR and the Human Research Facility. And we also learned how these things affect people and how they will help in the future of space exploration. We also learned about the scientific method and how you can even do experiments and research at home. Well, thank you for joining me today to learn about destiny and the scientific method, and I hope you get to watch the next video where we do some experiments hands-on. Thank you for watching, and I'll see you in the next video.